Okay, hello and welcome to this lecture, and in this lecture we will write a simple piece of MATLAB code for implementing this successive cancellation decoder. Once again, I want to emphasize we are not writing very efficient code which could be probably directly implemented on hardware or something. We are just writing something that works, okay, so that you can play around with it and use it for other sort of things. Okay, so what will it take to implement this decoder? Of course, you need a lot of representation, right, inside the code. How will you represent, etc. First thing you need to represent is the tree itself. So how do you represent the binary tree? So like I said, I will do it, the first thing I will use is this notion of depth. So this has depth equals 0, this level, and then you have depth equals 1, then depth equals 2, depth equals 3, depth equals 4. Okay, so remember this one is n equals 4 and capital N equals 2 power 4, which is 16. Okay, so that's this example. If you have a more general one, the depth will go further and further. So for instance, if it is 1024, the depth will go from d equals 0 all the way up to d equals 10. Okay, so depth is one thing. So this tells you at what depth you are, and then what about the node? Okay, the node numbering will start with 0 and then go 0 1 0 1 2 3. And then 0, 1, 2, 3, 4, 5, 6, 7, and then 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so these are the numbers. Okay, so at any depth d, you have nodes 0 to 2 power d minus 1. Okay, so it's easy to see. So even for d equals 0, this is true, right? So if you have depth d, you have nodes 0 to 2 power d minus 1 from left to right. That's one thing. So this is easy enough. I've represented each node, and then from each node, I need to know what its parent is, right? And I need to know what its left child is and what its right child is. Okay, so if you have node n at depth d, okay, so what is the left child, what is the right child, and what is the parent? That's my question. So you have so avoid some trivial cases. So we'll assume it's some sort of an interior node, so that you don't have the issue of leaf or root. Root has no parent, leaf has no children. Okay, so we'll assume some interior node. So that node n at depth d, what is the left child, what is the right child, and what is the parent? Okay, so you can look at it very closely. There is a pattern here. Whenever you see the node, the left child is always multiplied by 2. Okay, so this is going to go 2 times n, okay, at d plus 1, right, the next depth. Okay, what about the right child? Again, there is a very simple pattern. You can quickly observe it. It's possible to prove these things if you like rigorous proofs. 2n plus 1 at d plus 1. Okay, so left child is 2n, right child is 2n plus 1. So what is going to be the parent? Parent is floor of n by 2 at d minus 1. That's it. Okay, so you see what floor is. Floor is you divide and throw away the remainder. Okay, so that's what happens if you want to go to the parent. Okay, so it's easy enough. So once you have this notation of depth and node number from left to right, you can figure out easily what the left child is, right child is, and the parent is. Okay, so this is something important. We need to represent the binary tree, and this is how we will represent the binary tree. Okay, so that's first part of representing the decoder. We are not done. There's lots of other data that flows into the decoder. We need to represent that as well. We will see how to do that going along. So first thing we will use in the decoder is a representation for the nodes like this. Okay, and the next thing is the messages. Okay, so what are the messages that need to be stored? So if you remember, in the encoder, we had the u at the bottom, and then it got pushed into the next depth, next depth, next depth, and all that till it got to the root, and there was no need to store any intermediate things. It was just going in one direction. But the decoder doesn't go in one direction. Okay, excuse me. The decoder doesn't go in one direction. It doesn't go just down. Okay, it goes down, then it comes back up. And remember, when it comes back up, every node still needs to remember what its incoming message was. Okay, you can't forget that, because so for instance here, if you look at this node, okay, it first receives 8 beliefs. Okay, these are some 8 numbers. Okay, it processes it and sends out 4 beliefs to its left child. So it cannot forget its incoming 8 beliefs. Why is that? Because when the left child sends back its decision, it uses the incoming 8 beliefs and computes the G function. Okay, so you have to do that. Okay, but of course, when both the left and right child have sent their decisions, you can forget about what is there. Okay, so it is possible. So you don't have to store everything, but we will be a bit relaxed about it, and we will store all the messages that are flowing in every depth. Okay, so if you see here, you have depth 0. Okay, you have beliefs. There are 16 beliefs. Okay, maybe I should write it a bit differently. So what I'll do is I'll keep this as a shorter window, not a full screen window, and then also open up journal here so that I can do something. I can write on journal as well, and then you'll see something a little bit better. Okay, so let's do this. Okay. Okay. So this is the slide. So what about the received values? So if you look at this is the beliefs. Okay, so you have to store the beliefs. So how do you store the beliefs in the decoder? So if you look at depth 0, okay, and node 0 has 16 beliefs incoming. Okay, it needs to store all that. Then if you look at depth 1, node 0 in depth 1 has 8 beliefs, and then node 1 has 8 beliefs. These are all incoming. Node 1 is sort of not immediate, eventually it happens, but it has 8 beliefs. Likewise, at d equals 2, you can see node 0, node 1, node 2, node 3. They have 4 beliefs incoming each. Okay. So basically, in every depth, you have 16 beliefs. Okay. In every depth, you have 16 beliefs. They are associated with different nodes, but the total is 16. Okay. So what we will do is, we will have a 2-dimensional array L of let's say in this case 0 colon, I'll use this notation, 0 colon 3, okay, and then actually 4, right. So go all the way up to 4, and then 0 colon 15. Okay, this will be the 2D array. But remember, I am indexing from 0 in MATLAB. You have to do that minor adjustment to index from 1. So I'll just I'll use 0 for now, and you will see later on it's easy to make that adjustment in MATLAB. Okay, so I'll have a 2D array which stores all these beliefs. Okay, so that's important. So once you store these beliefs, you can associate the nodes with them. So for instance, node n at depth d, okay, its incoming beliefs, these are all incoming beliefs, okay, are in L of d comma, okay. For node n, it will be so 2 power d, if you remember, is the incoming. So maybe I should say that as well. I didn't maybe say that. For a node at depth d, the incoming belief, I mean, so I have done that here. So it's basically 2 power d, right. So okay, so node at depth d has it's not 2 power d, it's 2 power n minus d. Okay, so let me just use this notations, 2 power n. Okay, so I'm using too many n's here, so maybe I'll make this node I. Okay, so n is 2 power n. Okay, so if you have depth d, node 0 has 16 beliefs, right. So a node at depth d has as 2 power n minus d beliefs as incoming beliefs. Okay, so hopefully that's clear to you. And so if you look at node I at depth d, the array entry it will correspond to is L of d, it will be in the dth row, and then what will be the columns that will be important. So it will be 2 power n minus d, okay, so times I colon 2 power n minus d times I plus 2 power n minus d minus 1. Okay. So, this will be the 2 power n minus d beliefs associated with the node I. Okay. So, hopefully that is clear to you. So, for instance, maybe I can use this example. So, if you have L here, so this is if you think of a array here, so it will have the entry 0, 1, 2, 3 associated with node 0, and then 4, 5, 6, 7. These 4 are associated with node 1, okay, and then 8, 9, 10, 11. These 4 are associated with node 2, and then 12, 13, 14, 15. These 4 are associated with node 3. Okay, so this is the dth row of L. Okay, hopefully that's easy enough to see. So you just group all of them together in one array, but you associate different blocks to different nodes. So this is just for ease of storage, so that we can refer to this when we want to. Okay, hopefully this is clear. So we will use this array L, which will be a 2-dimensional array. So in general, it will be in general it will be L of 0 colon n comma 0 colon 2 power n minus 1. Okay, so that will be the size of this array, and the depth d is associated with 2 power n minus d incoming beliefs. And how do you store those 2 power d? I mean, you store it as one row vector, but different chunks of it you associate with different nodes. Okay, so this is how we do the beliefs. Okay, so we have represented the tree. We know how to go from one node to the other in either left child, right child, or parent. We have figured out how to store the beliefs. Okay, maybe not the most efficient. I'm sure you can find a lot of holes in how you can simplify the storage. You don't need to store this much, etc. But like I said, I'm not trying to write the most efficient code here. And the third piece of information that we need is some sort of a status for the node. Okay, so if you remember, a node comes into operation only once in a while. It gets activated, and it can be in different states, right? The state of a node, it may be never, maybe it's never been activated so far. Maybe it has finished step L, it's waiting for step R. Maybe it has finished step R also, it's waiting for step U. Maybe it has finished step U also, it's just done. Okay, so there are multiple states for the nodes. Okay, so for every node we have to store the state. Okay, so like I said, there are 3 things you have to worry about. One is representing the binary tree, being able to traverse. We figured that out. Next is storing the beliefs all through the tree, and we are doing some extra storage, just being very generous here. And then the third part is storing the states of the nodes. Every node will be in different state as it goes through the decoder. Okay, so you have to store the state. Okay, for states we will use a slightly different notation, just to be a bit more efficient than just just using some big 2D array. We could use a big 2D array as well, but I'll be a little bit more efficient with the nodes to make things easy. Okay, so let's first summarize what the states are. 0 is yet to be activated. Okay, 1 is finished L. Okay, 2 is finished R, 3 is finished U. Okay, so this is just my notation. There are 4 states to the nodes. It could be 0, not yet activated. So initially all states will be 0. I mean, all nodes will be in state 0. Okay, and then once you have done L, it goes into state 1, and once you have done R for that node, it goes into state 2. Once you have done U for that node, you know what these L, R, and U are. There are 3 different steps that we do on the node. It goes into state 3. Okay, once it goes into state 3, it's done. Okay, so this is how you will store the node, and then how are you going to store the states? Okay, so how do I store the states? So maybe I'll do something slightly efficient here instead of being very inefficient. So let's see. So we have, remember, so at depth 0 you have only 0. Okay, so I'll store the states in one linear array. Okay, so initially I have depth 0, and then I have this is depth 0, then I have depth 1. At depth 1 I have only two nodes, right, 0 and 1. So these two are depth 1, and then I have depth 2, I have 0, 1, 2, 3. Okay, and then I have depth 3, I have 0, 1, 2, 3, 4, 5, 6, 7, and so on, right. So this is what happens, and so on. So in general, node I at depth D will be at position, the position is, if you look at depth 3, it had 7 before, so it's going to be 2 power D minus 1. Okay, so that's 7 plus I. Okay, so remember the overall count is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, so on. Okay, did I miss anything? Okay, I don't think I missed anything. So it goes on like this. Okay, so so again, remember, I'm indexing from 0. This is one adjustment we'll have to make when we go to MATLAB. Change that. So node I at depth D is at position 2 power D minus 1 plus I. Okay, so if you think of depth 2 and node 2, it will be 3 plus 2, 5. Okay, so you will get the correct numbers. Node 7 at depth 3, it will be 7 plus 7, which is 14. Okay, so all of that will happen. So this is the state vector. Okay, and what will be the total length? You can compute. So what is the last node? D equals n. The last node will be D equals n, right? Depth of n, and node 2 power n minus 1. Right. So node 2 power n minus 1 at depth 2n. So that has position 2 power n minus 1 plus 2 power n minus 1, which is 2 into 2 power n minus 1, which is 2 power n plus 1 minus 2. Okay, so the overall length, so it will go from 0 to 2 power n plus 1 minus 2. Okay, so the length is this plus 1, which is 2 power n plus 1 minus 1. So that's the total length we need. So in fact, that's the total number of nodes in the binary tree. Okay, so the leaf has 2 power n minus 2 power n, then 2 power n by n minus 1, so on till 1. So that will add up to 2 power n plus 1 minus 1. Okay, so that's the total number of nodes. So we'll be a little efficient in storing the states. So once again, what is the state vector? Initially it will store all zeros, and once a particular node has completed a certain operation, it will switch into either 1, 2 or 3. Okay. So with this, we are ready to start writing the program. So now we know how to store, represent binary tree nodes and traverse from one to the other. We know that. We know how to store the beliefs and how to access the beliefs corresponding to a particular node. We know how to store the states of the nodes and access the state of a particular node, and we can start writing the decode. Okay, let's see. So over to MATLAB. So this is the encoder that we had before. It had the reliability sequence. You remember the encoder. So what I'm going to do is I'm going to save this as decode. So I'll call it SC decode just to distinguish from other things. So we'll have the reliability sequence. We'll keep it. We'll keep n as something small just so that we can do some debugging. Maybe keep this as 10. You get this, frozen positions. So Q1, the frozen positions, it's good to store the frozen positions explicitly. So I'll store them as f equals Q1 of 1 colon n minus k. Okay. So, because in the decoder you have to check if a particular index is frozen or not. Okay. So, for that we'll keep this f as the list of frozen positions, and after that the message and the u and the encoding can happen as before. So, right now you finished with the encoding, u is the code word, and you can transmit. Okay. So, let us transmit. For transmitting, let us just steal, so c word equals u. So, for transmitting and all that setup, let us steal some things from here. Okay. So, we will steal the EB over N naught, which has to be set up somewhere here. It's 0 dB, so I keep it at some 4 dB. Then you have these usual computations of rate and EB over N naught and this. I will have to change the rate calculation. What is rate for us? Rate for us is k by n. Okay, so I have done my sigma. Once I have my sigma, I have my code word, I can do transmission. Okay, so we can transmit once you have the code word. Okay, so R is there, that is my received value, but okay, so I guess code word is of length capital N, that is one change that is needed. Okay, that is it. So, we are done, we are ready to start the decoder. Okay, so we have the encoding, the reliability sequence, big fat one from the standard, and we set up the simulation, the frozen bits, code word, and we are transmitting. Good, we are ready to go. So, now the decoder, let us set up the storage. So, L, if you remember, is initially put zeros here. So, what is the total thing I need? I need n plus 1 rows, if you remember, that is the depth that we had. Depth goes from 0 to n, so you need n plus 1, and on this side it is just n always, right. And then the state vector, okay, I will call it ns. Okay, so these are the beliefs. So, this is the state vector, node state, and so I am calling it ns. This will be zeros of it is 2 power n plus 1 minus 1. So, that is 1 comma 2 into n minus 1, right. So, that is the state vector, node state vector. Okay, so initially it will all be 0. Once you have the R, you can initialize L of 1 comma colon equals R. Okay, so that is the belief of root. Okay, so that is true, and then the node I will use simply node equals 0, depth equals 0. Okay, so start at root. Okay, so maybe this one we'll put on top. Okay, that is it. We are quick to start. I will also have a variable called done, which will be 0 now. So, this will just indicate that decoder is finished or not. So, initially it is 0, which means it is not finished, and my loop here will simply say while done equal to 0. Okay, so, if it is 0, then you keep doing the loop. So, now this loop is just the traversal loop. Okay, just to keep the traversal going. So, remember I am starting at the root and I have to keep traversing. Once I have decoded all the messages, I can stop, but till then I have to keep traversing. Okay. So, what do we do first? First, I know what node I am at. I am at node and I am depth equals 0, node equals 0. I have to first check the state. Okay. Depending on the state, I have to do something. So, if so let me calculate the node position. Node position, if you remember, I just wrote it down here, 2 power d minus 1 plus I. Okay. It is 2 power depth minus 1 plus node node and then plus 1. Okay, why do I do the plus 1? That's the MATLAB adjustment for the position of node in node state vector, right. So, that is the npos, and then you have to do multiple things depending on whether or not npos is what is the state. Okay. So, you can do a lot of if conditions here. It is just a few states only. If ns of npos equal to 0. Okay, so, that is one condition. Else, so for now I will simply say display work in progress, we will write it. Else if, so it is good to end these elses. If ns of npos, where does it, okay, so I think I made a mistake here. This should be the wrong bracket. Ns of npos equal to 1, you have to do something, else if ns of npos equal to, actually else you do not need, I mean if it is not 0 or 1, it is going to be 2 and you know what to do. For now I will simply say display work in progress. Whenever it finishes, we will finish. Okay. Yeah. So, all right. So, depending on where we are, we do different things. That is good. Okay. And then, okay. So, that is nice. All right. So, even before all of this, I think one thing you can do is you can check whether you are leaf or not. Right. So, if you are the leaf, then you know what to do. So, this is assuming non-leaf. Okay. So, if you are leaf, there is a very simple thing to do here. So, we will put that code in a little bit later. So, for now I am assuming I am non-leaf. Okay, I am proceeding to do that part. If you are leaf, so you have to check that. So, how do you check that? If depth equal to n. Okay. So, if you have reached the last one, then you have to do something else, right. So, only if you are not so, you have to do this non-leaf stuff, right. So, let us push this to the right and then get an end here, so that things work out. So, I will just keep work in progress here, so that we will come back and write something there. Okay, so, hopefully, this is clear. So, how does that operation work? So, in every node I first check if I am leaf or not. If I am not leaf, I have to do something. If I am leaf, I just have to do I have to make a decision and then do something. Only if I am not leaf, I do anything. Okay, so, let us start on this. So, if I am not leaf, I am in state 0. Let us see how to write this up. Okay, so what do I do? I have to do min sum, and for min sum we have this simple the small little f function and the g function, right. So, one of the things I like to do is to write these f and g functions as these MATLAB inline functions. So, we can write f as AB is so I do not want to use the MATLAB sine function. The problem with MATLAB sine function is it gives the 0 for 0. So, that is not very nice. So, maybe we can do this modified thing, right. So, we can say 1 minus 2 times a less than 0, right. So, if a is greater than or equal to 0, no, maybe I should put here, yeah, a less than 0. Yeah, this is good, because then if a is negative, this is going to be minus 1. If a is 0 or positive, this is going to be plus 1. Okay. So, this times 1 minus 2 times. So, it is good to, I should assume that a and b will be vectors. So, I will put a dot product here and then dot into min of ABS of A, comma ABS of B. Hopefully this will work. It's correct. Okay, so this looks okay enough to me. Sometimes I like to check if this will work. Min of, for instance, 1, 2, 3, 2, 1, 5. Hopefully it will work. Yeah, it works. Okay. It's good to check once in a while that what you're writing is correct. So this is f. Okay, so this is the f function. If you remember, it does the min sum. Okay, for general vectors also it will work. Then I also need the g. G has three inputs, A, B, C, and its output is considerably simpler. It's B plus 1 minus 2 into C dot into A. This is the g function. Okay, so you remember the g function, it does just R2 minus R1 or R2 plus R1 depending on whether or not C is 0 or 1. Okay, so that's G and F. Okay, so once you write G and F, this is easy enough to write down. So we just have to figure out what A is and what B is, right? So what is A? Remember, for node and depth, we know what is the corresponding L value. So L node equals L of depth plus 1, comma, right? You remember the little formula that I wrote down? Right, so it's 2 power n minus d times I from, and then 2 power n minus d times I plus this guy, right? So this 2 power n minus d keeps appearing quite prominently, so it's probably worth computing that first. Okay, so I'll call it temp equals 2 power n minus depth. Okay, and then this is going to be temp times node plus 1 colon temp times node plus temp, so it is just let it go up to node plus 1. Okay. Okay, so you can do a few sanity checks. For instance, if depth is 0, node will also be 0. Okay, so this temp will be just 1. Okay, so at depth 0 I get 1 comma, so node is 0 and temp is 1, so it will go from 1 to 1 to 1. Okay, so I think that's okay, because the first time no, I'm sorry, if depth is 0, temp is 2 power n. Okay, so it will go from 1 to 2 power n. Okay, so I think that's okay. Temp is 2 power n, node is 0, so it will go from 1 to 2 power n. So it seems fine. So Ln is my incoming beliefs. Okay, so I've pulled it out of the storage. L is the storage throughout. I've pulled it out. I've got Ln. Okay, and then I can pull out this A and B, or maybe I can write it out explicitly for the next one, right? So maybe I should do the A and B. A is Ln of so what is the length of this? The length of this is temp. Okay, so Ln of 1 colon temp by 2. B is Ln of, okay, so I've pulled out the corresponding thing. So temp by 2 plus 1 colon end. Okay, so this is the A and B. Okay, and so we are ready to write down now what the next node should be. Node equals, so once so if it's non-leaf and I'm at state 0, I have to proceed to the left child. How do I go to the left child? Node is node into 2, depth is depth plus 1, right? So that's what we do. And once you have the node, new node, you have the new temp. Okay, so you've gone down in depth, so temp will become temp by 2, right? So it's one step down. Okay, right. So, initially I was at a certain the incoming belief length, the belief length is going down by 2, and then now I can assign what it should go in L of depth plus 1, comma the same thing, temp into node plus 1 colon temp into node plus 1 equals f of a comma b. Okay, that's it. So, this was the this is the next node, split beliefs into 2, next node incoming belief length, next node remember is left child, for left child, and then min sum and storage, right. So, you have to do the min sum calculation and store it back also, that is very important. So, this is the step for state 0. Of course, you have to change the state, ns of n pos should become okay, as soon as I do this, ns of n pos should become 1. Okay, so, this is done. Okay. So, hopefully, you saw how this was done. So, I am going to cut this lecture at this point. We will come back and in the next lecture see the other steps and how they work, and also we will check how this is working correctly a little bit later, but this is a good point to stop this lecture and do the coding in the remaining next lecture.